Looking at waves, when we're talking about waves, a wave is a transfer of energy through a medium. And so it goes through the medium. A medium is anything that it can travel through. So like air, water, something solid. In space, you can't send a wave because there's nothing for it to travel through. And it disturbs the medium but doesn't bring it along. If you think about sitting, let's say you're sitting on a little floaty thing. Here's your stick person, middle of the summer, just kind of hanging out. And a wave goes passing through, the wave will pass through and keep on going, but you'll stay in your same spot. So the water is disturbed, it moves you up and down, but the wave keeps on going, it doesn't bring you with it. We've got two types of waves. The first one is a transverse wave, and a transverse wave would be similar to what we have up here. The medium is disturbed perpendicular to the motion of the wave. So if I have a transverse wave and here's my surface, the medium, as the wave goes through, would go up and down and up and down and up and down like that. And then it would continue on and everything would go back to a nice flat surface again. So transverse wave, the motion of the wave is up and down, or the motion of the medium is up and down while the wave goes that way. Those two are perpendicular to each other. With a longitudinal wave, the medium is disturbed parallel to the motion of the wave. And so if you have a longitudinal wave, we usually don't draw them very much, but when we do, it looks something like this, where you have a tight area, and then it relaxes and spreads out, and then a tight area, and then it relaxes and spreads out, and then a tight area, and then it relaxes and spreads out, and then it keeps on going in that pattern. And while that happens, where it's tight and spreads out and tight and spreads out, it isn't super helpful in the way of drawing it. And so know how to draw this, know what it does, but it's not something we'll use quite as much with as a transverse wave. If you look at this, the wave might be traveling that way, and the motion of the particles are just back and forth here. So this moves there and there and there and there and there and there. But the energy of the wave as a whole would continue down the line. When we talk about drawing a wave, there's a few different things that you need to know about this. First of all, this would be a transverse wave, and this is the one that we'll use the most in the way of drawing. When you go from the relaxing point up to the peak here, this is your amplitude. I'll label that A, we'll write it out, P-L-I-T-U-D-E. And the amplitude will be the same up as it is down, the same measurement up as it is down. And it is the measurement from the resting point to the peak or down to the trough. So if we look at this wave specifically, we can count our boxes up. 1, 2, 3, 4. So the amplitude here would be 4. In this case, we're talking about boxes. You could do this with meters, you could do it with centimeters, millimeters, whatever that might be. It's a measurement of up and down. It's not one we'll use in calculations, but if you're talking about sound, it would actually give you the loudness. And if you're talking about any wave, it is corresponding with the energy that's found there. The wavelength is the distance of one complete wave. And so what we have here when we're doing this is, let's say I start here, and one wave would be the top, including the top and the bottom half, before it would start over again. So I go here and here, and then at this point, I would start repeating what I've already done, repeating what I've already done. And so one wavelength would go, if I label it on here, comes down, this would be my wavelength from here to here, okay, across that way. And so if we talk about, so the wavelength, in this case, if I count from here to here, I start here and I have 1, 2, 3, 4, 5, 6 boxes. And if I talk about the number of waves, I would have 1, 2, 3, 4, and this would just give me a half. So I would have 4 and 1/2 waves here. Looking at some of the definitions that we have in general, when we're talking about waves, our wavelength is and that's what we were just talking about up here, going from here to here. It's the length of one complete cycle. And when we're talking about our amplitude, we're talking about the distance from the resting point to the peak. The equation that we have when we're dealing with waves is that V equals F lambda. V measures our velocity in meters per second, just as it has in other times. F is frequency, and it's measured in hertz, and I'll talk about that in a moment. And lambda is our wavelength, and that's measured in meters. It's very specifically the length of one cycle of the wave. When we talk about frequency in hertz, hertz are equal to 1 over seconds. So if we talk about velocity measured in meters per second, frequency in hertz, so 1 over seconds times meters, we take the meters times 1 over seconds, we get our meters per second that we have for our velocity. So an example would be a wave travels at 190 meters per second. It has a frequency of 38 hertz. We need to calculate the wavelength. So 5 steps, we would put down our variables. 190 meters per second for velocity, frequency, we have 38 hertz, and we're looking for lambda here. We'll have to rearrange the equation, and so we want to get lambda by itself. We'll divide both sides by frequency, and so we'll have lambda equals V over F, and then we'll take, and we'll say of our velocity is 190 meters per second, divided by our frequency of 38 hertz. When we take that and divide the 38, we end up with 5, and lambda we'll measure in meters. We'll have 5 meters for our wavelength here. That's what we've got. The other way of doing this would be to use the triangle method, if that's something that you like. We'll put the V up top, and then F and lambda. And so you'll cover up whatever you're looking for. We're looking for lambda. If you cover that up, you have velocity divided by your frequency. Either way is fine for what we're doing. When we're talking about period and frequency, period is the amount of time for one wave cycle, and we measure that in seconds. And frequency is the number of cycles we have each second. And so because of this relationship, we have that our frequency is equal to 1 divided by the period, and the period equals 1 divided by the frequency. So they are both the inverse of each other every time. And sometimes we're in a situation where we know one and we can find the other, and sometimes we're in a situation like this where you have a bunch of waves in a bunch of time, and we have to figure out the frequency and the period from there. So in this example, we have 400 waves, and they go by in 20 seconds, and we need to calculate the frequency. Well, frequency, if we look here, is the number of cycles each second. So we'll take our total waves over our total time. These are our wave cycles over our total time. 400 waves divided by 20 seconds, we would get 20 hertz. This would be the frequency that we have here. And the period would be the reverse of that, where we would take the total time divided by the number of waves. And so in this case, we would take 20 seconds divided by 400 waves, and we would get 0.05 seconds. And this would be the period of those waves. We can also take the equations that we have here, the inverse of that, and do the same thing. Once we know the frequency, we could say that the period is 1 over the frequency, and say 1 over 20, and we would still get 0.05, not hertz, it'd be seconds, because we're measuring the period there.